Even just the existence of galaxies is evidence that dark matter is there. We've also seen it from the lensing of light, because light gets bent, light falls in a gravitational field. So as light's traveling towards us, if it's going this way, but there's a cluster of galaxies in between, it gets sucked in by the cluster and it can focus towards us. And we've seen that focusing. And we have measured how much mass is in the middle because of that focusing. And we've measured it in so many different ways now that there's really no debate that there is something out there that needs to be explained. So we still, happy to accept it might be some sort of theoretical change that's needed. Most evidence points to probably a particle, but hopefully we're hoping that when we do figure out what it is some sort of jump in our knowledge, a revolution in physics in some sense that really brings together many different threads. My personal hope is that dark matter and dark energy will be explained once we can combine quantum physics with general relativity.
Welcome back to the Smarter Not Harder podcast, your home for 1 cent solutions to $64,000 questions. I am your host, and I'm back. I'm Jodie Duval. So on today's episode, we have a very special guest, Professor Tamara Davis. Now, Professor Davis is a renowned cosmologist and astrophysicist at the University of Queensland. Her research focuses on understanding some of the universe's most profound questions and mysteries, including dark energy, dark matter, and the expanding universe. She's involved in numerous international collaborations, such as Dark Energy Survey, and has received prestigious awards, including the Australian Laureate Fellowship. So in this conversation, we dive deep into her journey into cosmology and astrophysicists and how she got into it. And the child in me came out as well, just those big questions. We look up into the stars and just such a curious person. So I really enjoyed this conversation with Tamara. So we also look at her groundbreaking work on dark energy and the future of our universe. We also discuss the role of arts in education, at the intersection of cosmology and consciousness, and what's next in the search for a grand unification theory. Plus, we'll explore some fascinating questions like, what does the universe look like in terms of, does it reverse its expansion or increase its expansion? And what role does dark matter really play? So we have a really fascinating conversation in a topic I feel that's not covered often in a podcast. So it was very interesting to have this insight into physics and, cosmology, and just, I think we all have these questions when we look up at the stars, where are we in this world? And we talk a lot about Tamara's input into how she sees the planet. So we do talk a little bit about the future of our planet. And, we're really lucky to be here, so let's look after it. From her perspective, there's not many better planets out there that we can go and land on. So without further ado, let's welcome Professor Tamara Davis to the show.
All right. Welcome to the show, Professor Tamara Davis. Thank you so much for joining me today.
Excellent. Thank you so much for having me.
Cosmologist and astrophysicist. Does that not need any more introduction? It's just incredible. Wow. Your distinguished career is fascinating. But how did you land here? How were you drawn into this field? We all have these beautiful moments as children, particularly, because we don't have time as adults, looking into the stars and wondering how big that universe is out there. But you have now made a life out of it. It's just fascinating. So tell us, how did you land here?
Yeah, I guess that's a big one. I guess I feel like maybe I'm a big child, that I never lost that wonder for the universe. And I am ridiculously fortunate that I get to go and study it every day as part of my job. And so I think initially I never had any, some people have these great grand plans of what they want to be when they grow up. I never had any such great grand plans. I was just insanely curious about all sorts of different things. And I remember as a kid seeing Halley's Comet. My parents took me out onto a houseboat and me and my siblings, and they took us out at night, and they said, this is going to be back in 75-ish years. And my little brain, as a 10-year-old or so, was going, how on earth can humans possibly know that that's going to be back? I think that I remember being my first spark of curiosity about not the beauty of the sky or the thing like that, but just how we understand the universe around us and how much we can know. And that was insanely fascinating for me. I always loved science fiction, sort of books and like thoughts of travel to space. The space shuttles were all the thing, like new-ish stuff as I was growing up. And I remember studying them as a kid and like learning all about it. And then when I got into high school, there was a teacher who told me about the fact that time and space aren't fixed, that they can warp and vary, and like you can get time dilation and different people will see clocks ticking at different rates. And again, mind blown. That was just so fascinating. And I'm like, I want to study that. That sounds cool.
When I was reading your bio and your website and your research, and I was like, how did I not know that this existed? I would have studied this.
Yeah.
Oh, and even my son, I was asking him a day, I'm like, guess who I'm interviewing soon? And he's like, who are you? I'm like, an astrophysicist. And he's like, oh yeah, I know about grand unification theory, Mum. And I'm like, what? Oh. So yeah, I guess, there's been so many amazing things that you, again, like prestigious awards, your research into dark matter, dark energy, cosmology sort of tackles some of the biggest questions about our existence. And I really want to dive into, what that means for us here on Earth. And I know you have some involvement in many different areas of that as well. So, but let's just start with dark energy and dark matter. And these are the biggest questions that you obviously have. And when I was reading about this, there's been just some so fascinating of the expansion of the universe, and then maybe the big crunch, or so there's so many varying theories. So I just can't wait to hear about this.
Yeah, so cosmology, a lot of people don't really know what it is. It's the study of the universe as a whole, like the study of the big picture. How did the universe begin? How is it going to end? And everything that happens in between. What we're doing with cosmology is really trying to understand the fundamental laws of physics that govern our universe, figure out what our universe is made of, and put that all together into a big picture so that we really understand the context of our lives here on Earth. The connections with our lives here on Earth come in a variety of different ways, because it's by understanding more about the fundamental physics, we gain more capabilities as humans, whether that's gadgets, different types of imaging, this, that, and the other. Even things like studying black holes and general relativity doesn't necessarily seem to have any direct applications. But if we didn't understand the relativity, if we hadn't tried to understand these sort of fundamental questions about what's going on, we wouldn't understand time dilation. And do you know the most common use of time dilation in everyday life? The fact that clocks tick different. There's something that you may have used even today. I don't know. If you've navigated with a little blue dot, on your maps, the GPS satellites are in a different gravitational field than our clocks here on Earth, and they're moving fast. They're orbiting the Earth. And both of those things cause time dilation. So if we understand the theory of black holes and how time dilation works for those type of things, we wouldn't have understood how to make the clocks sync correctly for GPS. And so there's like some interesting things like that you get that you wouldn't have necessarily realized were connected to, say, black holes.
Yeah, no, absolutely. And again, like my knowledge in this is sort of minute and childlike. But so I guess some of the biggest questions, obviously, is that expansion. I was reading some of your information around that. Maybe talk to us a little bit more about that in terms of trying to solve these big questions of like, how much expansion is there? Or is it going to then go into oneself? And then what does that mean for us? Is that how many universes are there out there? And, all these questions, it's just obviously to talk about in one answer. But what have you discovered? What have you found? What are some of the things now that you're also still wanting to know that haven't quite been answered? And I'm sure there's lots.
Oh, that's just a small question you're asking there. I think it's interesting to think back. 100 years ago, we didn't know that the universe was expanding. So we didn't have this picture of an expanding universe. In fact, people were looking at these spirally cloud things that they could see through their telescopes, and they didn't know that those were galaxies at the time. They didn't have that name. They called them spiral nebulae because they thought they were maybe clouds of gas in some sort of spiral shape really close to us. And then there was this big debate over whether that was true or whether they were actually really far away and there were whole systems of stars that were in the distance. And so we now know that we live in a galaxy called the Milky Way, and we know that we're just one of hundreds of billions of galaxies in the observable universe. My great-grandparents were around for that, discovery. It's still, in some senses, really quite recent. As soon as people realized that they could measure distances to these things, they also measured the speed with which they're moving. You use the spectrum of light. You take the light from these galaxies and you make the sort of rainbow of colors come from it, like putting them through a prism. And you look at like lines in their spectrum and you can see where the lines shift. And if they've all shifted towards the red, the thing is moving away from us. The same way that the police catch us for going speeding in our cars if they're using the radar guns. It's the same effect. So we measure their speed and their distance, and that was done first in the late 1920s, and that was the measurement that the universe is expanding. So that was a big discovery, and people like Einstein were surprised by this. He famously had added a term to his equations to allow for a static universe, because his equations predicted that the universe had to be expanding or contracting. But in the early 1900s, people were looking up and they could see the stars and they were like, they're not moving away towards us. But they just hadn't looked far enough yet. And so this might be a false story, but Einstein apparently said that like putting that term in his equations to allow for a static universe was one of the biggest blunders of his career, because he could basically have predicted from theory that the universe had to be expanding or contracting. We are, as a physicist, guided by observations, and the observations at the time hadn't shown that yet, because we just hadn't been able to see far enough away. So anyway, that's like 100 years ago. Fast forward to the 1990s, and people were still trying to answer a question that had arisen right from the beginning, which is the universe going to expand forever, or is it going to recollapse? Now, that question is asking, do the galaxies have enough gravity? Are they heavy enough to pull on each other enough to stop the motion away and make the motion come towards? So it's actually similar to me asking, if I'm standing on the Earth and I jump up, gravity pulls me back down, right? But if I was to jump fast enough, I would have the escape velocity and I would be able to escape Earth's gravity. Here on Earth, that's 11 kilometers per second. So the question was, do the galaxies have enough velocity to escape from each other's gravity, or are they going to be pulled back together? So in the 1990s, people went out to measure this, and they used supernovae, these exploding stars, as indicators of distance. You can measure how bright they appear, and that tells you, because we know how bright they are intrinsically, you can tell how far they are away. And so they measured this expansion over vast distances and looked back into the past, because when we're doing astronomy, you're looking back into the past. The light has taken so long to get to you that we're looking back billions of years sometimes. And they measured the expansion rate billions of years ago and compared it to the expansion rate now. And that was the measurement that showed that the expansion rate has been speeding up. So something out there is causing gravity to push instead of pull. We don't know what it is, but we give it the name dark energy. And that was discovered basically as I was starting my PhD. And that shaped my career, because that's what I've been studying ever since.
Pardon the interruption. This podcast is proudly brought to you by Home Hope's Metabolomics module, a groundbreaking framework pioneered by Dr. Ted Ashokoso. So while we've been discussing some of these cosmic mysteries with Professor Tamara Davis, let's not forget about the mysteries within our own bodies. Home Hope goes beyond traditional medicine, focusing on detecting and correcting imbalances for optimal health. So our metabolomics module dives into the intricate metabolic processes of the human holobiome, combining advanced metabolic testing with a holistic approach to wellness. So ready to optimize your client's health? Then visit homehope.org, products metabolomics, to learn more, and use the promo code podcast10 for a 10% discount on metabolomics module or any other certification from Home Hope. Now, back to our cosmic conversation, armed with knowledge to optimize both yours and your understanding of the universe.
So it's not known actually what that is in any shape, way or form or energy, or so it doesn't really have any other validity or preface as such, so it's just referred to as the dark energy or dark matter.
Yeah, so that's dark energy, and I skipped over dark matter, so I'll come back to that one. Dark energy is the name we give to whatever it is that's causing the expansion of the universe to speed up, or the apparent speed up of the expansion. So that encompasses the possibility that it's actually not an acceleration. We've just stuffed up the measurements. We've interpreted our measurements wrong, and there's some sort of theoretical thing that we need to fix. It encompasses that Einstein's theory of gravity needs revision, that maybe things aren't behaving as we expect, but also that maybe there's some sort of fluid out there or some sort of gas of particles or something like that has some sort of repulsive gravity property. And again, this is one of the reasons we study this, because if something like that is out there, even if it's a mistake in our theory or if it's a real sort of physical thing that's has a repulsive gravity instead of attractive, maybe we can harness that. Maybe it's a clean source of energy. Maybe it's a source of propulsion. Maybe we can't ever harness it. Maybe it's too weak for that. But that's one of the reasons we study it, because we don't know. And so dark energy is the placeholder name that we give to whatever it is. And what we're currently doing is trying to measure it more precisely, measure its properties, whether it's the same everywhere, whether it clumps, whether it's different in different directions, whether it's changed with time, all of these things, to try to nail down which theories could explain it.
So this is the Dark Energy Survey, am I correct?
Yeah, so Dark Energy Survey is a project that I've been part of that's one of many, many projects around the world that are trying to measure the properties of dark energy more precisely. Recently, we published a catalogue of about 1,500 of these exploding stars, and that was a really big advance on any data set that had existed before. It sort of makes up 80% of the known supernovae beyond the redshift 0.5, which is a measurement of our distance. Much more distant supernovae than we've ever seen before. So with this, we've been able to characterize the expansion over a longer time more precisely. And we wanted to test whether the dark energy is constant with time. And this actually relates back to Einstein's biggest blunder that I was talking about earlier, because that term that he added to his equations to allow for a static universe was one that had a repulsive sort of gravity that was something potentially vacuum energy, like the energy of empty space itself, or what he called is a cosmological constant. And it's just this constant, gentle outwards force that could counteract the gravitational pull of galaxies towards each other. And until this year, basically everything we had seen from all of our data had indicated that actually was consistent with what we were seeing the behavior of dark energy to be. It seems to be this gentle outwards pull. It's the same push. It's the same everywhere. And it could just be the energy of empty space itself. For some reason, and quantum physics does predict this might be the case, vacuum actually has a repulsive gravity. And our data this year, supported by another project, the Dark Energy Spectroscopic Instrument, which is another one we're part of, but it maps the distribution of galaxies instead of measuring supernovae. Both found the same thing, that there might be a little bit of time variation in the dark energy, and so that cosmological constant might not be the final story.
So on the galaxies as well, growth, change, as you say, like the consistency or the amount of galaxies, I'll comment on that. That's one of my questions without knowing anything more about this.
Actually, even before the supernovae showed that the universe was accelerating, there was a hint from just counting galaxies that was the case. And that's because people had just you go out and you look through your telescope, you look at this patch of space, this sort of volume of space, and you count how many galaxies you see in it. And you do that far away and you do that nearby, and you don't expect on average there to be much difference wherever you look. On average, if you take the same size volume of the universe, you'll get approximately the same number of galaxies, because the galaxies are sort of spread relatively evenly around the place. And people were finding that there were too many galaxies far away. And if you put the number of galaxies divided by the volume of space, that sort of number density was too high far away. Now people were galaxies merge. Maybe there's just the merger rate is bigger than you think. And, maybe that's the reason. But it turns out that the number count of galaxies wasn't the wrong thing. The volume was the wrong thing, the thing that you divided it by. Because if you took into account the acceleration of the universe, the patch of the universe people were measuring was bigger than they had thought, because of the acceleration, the change in distance because of the acceleration of the universe. So actually the number counts of galaxies, the distribution of galaxies was evidence even before the supernovae that the universe was accelerating.
Gosh, that is so fascinating. So as with any, big questions, there is always, a debate, I guess. So what have you seen, and has there been any valid debates against what you are trying to prove or ask questions of? And I guess it's, a huge part of science, outcomes and have it proven or disproven.
Yeah.
So what have you seen there?
So there was a cool debate early on when people were looking at the expansion of the universe just to determine whether there was a Big Bang or not. So if everything was expanding from a really hot, dense state in the past. And there was a competing theory called the steady state theory, which said that the universe doesn't change with time on average. As it expands, more matter is created in the gaps, just from nothing. And it always stays approximately the same density. And this was a hypothesis that was taken very seriously. And one of the reasons it was taken so seriously is that early measurements of the expansion weren't very well calibrated. And they thought that the expansion was going really fast. And that to get to sort of the size that we currently see it, or to get to the rate that we see it, the universe would only have to be a couple of billion years old. That people already understood from rocks and fossils and stuff that the universe was older than, or that the Earth was older than that. And you can't have the Earth being older than the universe. So people were like, oh, maybe the rate that we're seeing for the expansion actually is just constant all the time, and there wasn't a Big Bang, and, et cetera, et cetera. That could possibly explain this age discrepancy. But that debate went away when we realized that, one, the expansion rate wasn't calibrated very well. So when people measured it more precisely, they found out that it's going at a rate that's compatible with the age of the Earth. And also, people measured something called the cosmic microwave background, which is a direct measurement of the light that's left over from that hot, dense early state. So it's basically from when everything we see in the universe was compressed into a tiny patch, and that was glowing. So if you lived back then, it would have been like living in the interior of our sun. It would have been like so hot and dense, but that the inside a star that expanded everywhere, like it would have been absolutely everywhere you went. So we can now see that. We see the light from that. So there is no question that there was a Big Bang, because we can actually see the glow from the bang, basically.
Yeah.
Yeah. So what other debates? There was a big debate over dark matter, about whether dark matter is a particle or a change in our theory, like if we need to adapt our theory of gravity. Now, I haven't explained dark matter very much, but dark matter was one of the things that was blindingly obvious. As soon as we knew these spiral galaxies were galaxies, people went out and measured their motion, and they were moving too fast to be explained by the gravity that you could see in the stars. So they just weren't heavy enough to hold themselves together in their orbits. And so that was the first paper on dark matter was in 1933, after the whole expansion was discovered in late 1920s. So it was it was really blindingly obvious that gravitationally something is out there that we can't see, or something is wrong there. Vera Rubin did an even better measurement in the 60s, 70s, measuring individual galaxies and their spin, and saw the same thing. So dark matter's been really persistent for basically a better part of a century now, that people have known that there's matter out there that we can't see. There was a big debate over what it was, and that debate somewhat still rages, but the consensus is now that we're relatively confident that it's actually some sort of particle, a particle that doesn't bounce off us, so it doesn't interact with electromagnetism, it doesn't have any charge, and so it doesn't, our atoms are mostly empty space, so it just goes whoosh straight through our atoms without bouncing off them, because it doesn't feel the charge, it doesn't know that it should bounce. So it doesn't really have pressure. And we think that makes up probably 25% of the universe, and then the stuff that makes up you and I, the normal, everything that we see on the periodic table, is about 5%. So the rest being, the other 70% being dark energy. So basically, we make up 5% of the energy density of the universe. And yeah, we're the icing on the cake. And the cake is all stuff that we can't see.
Yeah. And it speaks to, which I want to get into later, a little bit more on consciousness and those thinking questions for, where we belong here. And but that speaks for itself. The ratio there, we are much like this. Yeah. Yeah.
Perhaps, people are sometimes ask, does thinking of the universe make me feel small? But I would say, I'm as small compared to a galaxy as I am large compared to the nucleus of an atom. And so I figured that makes me about Goldilocks size. And also, there was a point when I was looking at it through a telescope and I saw something that was so far away that emitted the light that we were seeing well before the Earth formed, 2 times the age of the Earth ago. And the first thing that light had hit in that entire time, billions of years, was the mirror of our telescope. And it shows just how empty the universe is. And that was, if anything was going to make me feel small, that would probably be it. But I interpret that in a way of like, as humans, we're able to detect this now, something so faint from so far away. And as humans, we're able to understand what it is. And I understand that the light I was seeing was coming from a black hole that was gobbling up material and stars and falling into it. And as it fell in, it was getting really hot. And we know what that is now, and we can understand it. So I think rather than making us feel small, I think being able to understand the universe around us should make us sort of feel powerful. I think it's a really fascinating study.
Yeah, no, absolutely. It's so vast. I think that's why you can feel so small, because there is so much more there, but we have the capacity to and the ability to, as you say, study this and then to understand it. So yeah, that is quite powerful in itself. So was there anything more in terms of dark matter that you wanted to comment on or give more information on?
Yes, and like I gave a couple of early examples of dark matter. We've now seen it in so many other ways as well. So like the cosmic microwave background, the pattern of fluctuations we see back from the Big Bang wouldn't make sense without having dark matter as part of it. Even the existence of galaxies, it wouldn't be possible without dark matter, because it's the scaffolding. If you took away the mass of the dark matter, galaxies wouldn't have had time to form yet. The gravitational attraction would be too weak. So even just the existence of galaxies is evidence that dark matter is there. We've also seen it from the lensing of light, because light gets bent, light falls in a gravitational field. So as light's traveling towards us, if it's going this way, but there's a cluster of galaxies in between, it gets sucked in by the cluster and it can focus towards us. And we've seen that focusing. And we have measured how much mass is in the middle because of that focusing. And we've measured it in so many different ways now that there's really no debate that there is something out there that needs to be explained. So we don't know whether we still, happy to accept it might be some sort of theoretical change that's needed. Most evidence points to probably a particle, but hopefully we're hoping that when we do figure out what it is some sort of jump in our knowledge, a revolution in physics in some sense that really brings together many different threads. My personal hope is that dark matter and dark energy will be explained once we can combine quantum physics with general relativity. So our theory of particles and our theory of gravity, which we know currently don't really work together, where we're trying to figure out how to merge them. And that's an ongoing effort that's been going on easily since Einstein's time. We haven't figured out how to do that yet. But hopefully, my hope is that when we can do that, it will really reveal how the universe works in a much more fundamental way than we have now.
Yeah. Do you have any thoughts on how long that's going to take us?
It's how long is a piece of string. It's one of those things like, it's funny when we're asking for grant funding and things. It can be sometimes difficult to ask for funding for theory to like improve our theories, because you're like, I'm going to sit down and think about this hard for like 5 years. But if you're going to say, I'm going to go make a bigger instrument than anyone's ever done before, measure billions of galaxies and increase by an order of magnitude the number of galaxies that we've measured, it's a really clear milestone, and you know whether you've achieved it. Getting funding to actually do the thinking part of it can actually be a bit of a challenge. But yeah, you can't do one without the other. You can't. Observations are useless unless you interpret them. So the question of when we're going to figure it out really depends on when someone has that aha moment where it comes up with a theory and everyone's like, oh, of course, that is clearly how it worked. It would be an exaggeration to say that's how relativity was received early on. But these days, if you look at relativity and quantum physics, quantizing physics, quantizing particles, meaning that matter's made of particles and they've got distinct energy levels and stuff. That was just so clearly sort of right. It explains so many different things simultaneously that it's very, very well established. And similarly, the fact that time warps and bends and you've got this relativity thing, it actually comes from a really sound philosophical principle, the principle that physics experiments should look the same no matter where you are, how you're moving, or which direction you're pointed. And if you assume that, relativity sort of falls out just as a consequence. Mm-hmm. So we don't have that really neat theory for how to combine relativity and quantum gravity yet. And until we have that aha moment, and we don't know when that's coming, or if that's coming, if we even have the capability of figuring that out. So that's what we're striving for, though.
That's why we're here. Let's spread this word. We'll ask you where we can help. But ground unification theory. Talk to me a little bit about this and what that means. And obviously, we're trying to look at unifying the fundamental forces of nature as such. So, what's all this? What is this thing?
Well, it's very much basically what I was just talking about, because we have our theory of quantum physics and we've got quantum chromodynamics, like color dynamics, etc. And it has the weak and the strong and the electromagnetic force all involved, and it explains all of those simultaneously, and it shows how those are actually interlinked, like they're related to each other. And then over here we have gravity. So these days we say that there's 4 forces of nature, often, which are you have strong, weak, electromagnetic, and gravity. Now, I actually was asked at a trivia quiz once. The quiz question was, what are the 3 forces of nature? And I was like, oh no, what could they possibly be looking for? And so I was like, what textbook would have given someone the impression that there were 3? And so I answered electricity, magnetism, and gravity. And sure enough, that was what the quizmaster was looking for. Because if you go back over 100 years, electricity and magnetism were thought to be separate forces. Right. But now we know that they're actually the same thing. They're both related to charges. Some are charges going through a wire and some are charges in a magnet with a positive and negative end. But they're both the same force. And so that was like electromagnetism became like one thing. And strong and the weak are all part of quantum chromodynamics. They're sort of also related to the other part. Like they're all sort of together. But gravity sits out over here. It doesn't sit with the others. And one of the reasons is that all of our theories for the quantum side have a fixed time and a fixed space. And those are in the equations and they can't warp and bend. Whereas general relativity requires time to be dependent on the observer. And so there are attempts to merge those. So string theory is one attempt, loop quantum gravity is another. There's a variety of different ways that people have tried to make a theory that simultaneously explains both the quantum world and the gravitational world. And so that's what GUT is, the grand unification theory. It was to unify all of the forces.
Wow.
Sorry for the interruption again, but I have an exciting announcement. And this episode is proudly brought to you by Transcriptions, the leading provider of precision-dosed, physician-formulated pharmaceutical-grade formulas in the form of a buccal troche. And as we explore the vast mysteries of the universe, let me introduce you to TroCalm, a remarkable formulation from Transcriptions that provides precision-dose stress relief and enhanced mental clarity. With its precise dosing and expert formulation, it promotes relaxation, reduces anxiety, and improves sleep quality. Perfect for those deep thinkers among us trying to unravel the universe's mysteries, just like Professor Davis. If you're ready to take back your well-being and relaxation, then head over to transcriptions.com and use the code POD10 to enjoy a 10% discount on your purchase. Now, let's get back to the fascinating discussion with Professor Tamara Davis and dive deeper into the world of cosmology and astrophysics.
Yeah, no, it's just so fascinating. We are, looking at the universe and then fine-tuning conditions of life, and then there's obviously the Big Bang, and then there's so many different theories and people and thoughts around consciousness, and where that's, again, one of the most biggest questions. And is there more consciousness? Is there things outside of our galaxies or in the galaxies that we don't know about? So what's your opinion on all of this?
Consciousness, I think, is an emergent phenomenon, just as life is. Like, I think it's an emergent phenomena are really fascinating to me. It's how complex behavior can emerge from really simple rules. Our DNA is made up of 4 different types of base pairs and 4 different types of code. And you put that all together in different combinations and you get elephants and butterflies and grass and humans. And even within a human, you get hair and skin and eyes. And it's amazing how that can all work. And so I think consciousness is a similar thing. It once you have a complex enough system like a brain, the idea of consciousness can emerge from that. And so the universe in some ways is like a vessel for allowing emergent phenomena to occur.
Yeah, absolutely. Perfect way to put it. There's probably many things that you're thinking about all the time. I can imagine being inside your brain. But, what are the particular questions around either, philosophy or consciousness and cosmology, and how that looks like for questions in future that you want to have answered? Is there anything there?
Well, there's so much there. So questions of the origin of the universe and, how did the universe begin is a relatively philosophical one. A lot of people have philosophical opinions on that, but we can attack that scientifically and try and answer that question. And that also answers the question of where things are going, like how the universe could potentially end. And what is the meaning of our life? And is there any meaning? Those kinds of questions come under the cosmology remit to some extent. And other questions like, are we alone in the universe? So you mentioned consciousness elsewhere. Is there any other consciousness apart from our own? And one of the things we learn from studying the universe is just, it's vast and there's an enormous amount of planets out there. We've observed thousands of exoplanets now, so planets around other stars. We've even seen some that are getting close to Earth mass and that kind of thing. But if I've learned anything, it's really how special our planet is and how really special life here is. It's not obvious that life is abundant elsewhere. There's a question about whether, if life is out there, why haven't we seen it really obviously yet? So this is known as the Fermi paradox. And there's all sorts of cool possible explanations for that. Some of them aren't so cool. Some of them are, when a civilization gets intelligent enough to be able to build rockets to go off into space. That's also about the level of technology where you're building intercontinental ballistic missiles. And it may be that getting to a certain level, people just destroy themselves. That's one thing that people have contemplated. My favorite, though, is that we're actually in some sort of galactic zoo, and the other intelligent beings out there are sort of watching us from afar and going, "Oh, don't disturb them. Look, they're trying to do quantum physics. Isn't that cute?" But I mean, it would be hard to hide out there. And so whether intelligent life emerges from this sort of natural situation is a big question. But it's cool also that it's one of the things that we are now able to scientifically attack. So with things like the JWST, the big space telescope that recently was launched, you can look at planets and see their atmospheres slightly. You can see light from that star passing through the atmosphere, and we're hoping to measure the contents of the atmosphere and look for things like free oxygen that would be indicators of life on that planet. So not necessarily walking, talking, human-like life, but microbial life, that something like the cyanobacteria that would have been all over earlier. That's interesting.
Oh, so fascinating. And like you say, yeah, I can't believe we can actually be discovering and looking at those big questions now. Wow. It's just incredible. So onto this beautiful Earth that we are very lucky to be a part of. I know you are very interested in and advocate for a lot of sort of climate support or, information around that, and also women in science, which I wanted to talk to you about too. So obviously the STEM fields, or, as I've been asked, why isn't it called STEAM? Where's the arts? Where's the, but what does that look like at the moment for you in terms of women in science and then looking at the climate aspect of this beautiful Earth that we have?
Yeah, so the women in science thing, I'm absolutely privileged to be, there haven't been that many female physics professors, even now, relative to the number of men. Here in Australia, my university was the first university in Australia to promote a female to professor in physics, which is pretty good until you realize what year it happened in. I thought that it would be something really late, like 1975 or something like that. But no, it was actually the year 2000. So, there's some catching up to do, but it's never been a better time to be a woman in physics. And I've felt entirely supported my entire career, and just immense support and encouragement from everybody around me, regardless of gender. And yeah, so there's a lot of attention now on things like unconscious biases, and that might not have been something that was realized before. And so I'm hopeful that if someone wants to study physics and stuff, they're going to be encouraged to do so and have the opportunity. Now, that's obviously not universal around everywhere yet, but there are a lot of opportunities at the moment, and I'm optimistic on that front.
Absolutely. And also having and inspiring others to be doing this and actually seeking that out if they have the interest in. But I agree, there's a lot of catching up to do. You can still see a lot of limitations. Yeah.
Yeah. I do remember someone, I think it was my second year of uni, where one of my parents' friends said, isn't that weird that you're doing physics as a girl? And I was like, no, I think it's pretty normal. But then that was actually making me went and go to my class and have a look around. And the first class I looked at, there was about 40 people in the class, 6 of which were female. And I was like, oh yeah, we are the minority. But this is probably a benefit for me. I was just oblivious to those kinds of things. But I've heard from women who found that intimidating. And so as things balance, it sort of snowballs, I think, as we have more and more mentors and leaders, and the numbers in the classes are a bit more equal.
Yeah, absolutely. So you do spend obviously a lot of time mentoring now and being involved in all of this, which is incredible. Yeah.
Yeah, it's a very rewarding part of what I get to do.
All areas then, and you get rewarding components through the research and then obviously through the mentoring as well. So it's beautiful. Yeah. So climate, talk to me about climate. Anybody predicts? What can we do? Are we doomed?
Well, so I don't study climate specifically, but what I have studied is conditions on different planets, and things like Venus that have a massive runaway greenhouse effect are a little bit terrifying. I don't know if you've seen the movie Interstellar. It was a big one that I know, I can't remember how many years ago. It's a bit old now, but so many people asked me about that, and it used wormholes to get to other planets, and they were trying to, we destroyed Earth and people were trying to get to other planets. And the takeaway message that I have from that movie is nothing about like that, the fancy physics to get there, or rather it is to ascend. And that the answer is that, it is incredibly hard to get to other planets, just like ridiculously hard. No matter how much fancy technology we get, it's really, really hard. And the other planets are pretty much guaranteed to be more crap than Earth when you get there. I mean, we've evolved for the conditions on this planet. That's part of the deal with evolution, right? We can see visible light because that's what our atmosphere transmits. That's what the colors that the sun is transmitting. We're evolved for this temperature, this atmosphere that's around us. Early Earth didn't have an oxygen atmosphere because that had to wait for plants to evolve. And so that the cyanobacteria and things like that oxygenated the atmosphere. And in some ways, they poisoned the atmosphere for themselves because they were carbon dioxide breathers. And so now we have oxygen breathers here. And so Earth has already had, waves of change of what kinds of life forms thrive on the surface. And when I look up and I look at all of the vast numbers of planets and stuff that are out there, the gaps between them are so immensely huge. And we have about 100 kilometers of air above us. That's the distance from where I am to the sort of the coast near Brisbane. It's really not very far. And that is all the air we're ever going to have to breathe. And so if there's one perspective that astrophysics gives me, it's that we really have to look after this planet because it's very difficult to get anywhere else. It's very precious.
Yeah, I love your outlook and I love your perception of it. And as you're saying that, for us not looking after this planet, this Earth that we are on, we are also inhibiting our own evolution because we are not able to evolve quick enough for the damage we're doing to the Earth. And I see it in my practice, as a health professional, from the amount of chemicals and issues that we're causing upon our planet. Therefore, we're seeing so much more destruction of our own health because of that. So really, it's just definitely a different insight or a different perspective on that. We don't have unending air to breathe or oxygen to breathe. We don't have unending trees and plants to help us produce them. So yeah, it's very fascinating. So what, I guess it's again, another big question. It's been a day of big questions, but what are the biggest things that we can be looking at to do from your perspective of what you've seen in your studies?
Well, I think that when you take the sort of astrophysics perspective and you look at the Earth floating in the blackness of space with this little tiny atmosphere with us to breathe, any other priority than looking after the Earth sort of fades into insignificance. And also those petty squabbles that you have with your neighbor or, oh dear, we wore the same dress to prom type of problems really sort of pale in insignificance. So I guess we sort of do know what we need to do to look after the planet. It's so hard to coordinate people and get everybody to act in their own benefit, because it's really obvious. We had this sort of fun debate, actually. Well, fun in a way. It was a comedy debate that I did with some other physicists, which is more certain, global warming or gravity. And we talked about, the consequences of the two. And the consequences of gravity are blindingly obvious. If I jump off a bridge, it's not going to end well for me. But if I make more coal-fired power plants, I don't notice immediately. It's not like I'm going to see a consequence a couple of seconds later. And that long-term thinking is really hard, and even for governments and small things. If you're looking in context of a few years, that's really hard to prioritize. But in the end, we really have to start learning how to get that big picture approach, and also think of humanity as a whole, really. Like, we're not separate countries, we're not individuals. Well, we are individuals, but we're not just individuals. We're a part of like this whole collective. So that, I think, is a really important perspective to help each other out.
Yeah, absolutely. And it's one of our weaknesses, I think, is that we don't have that collective consciousness. We have that one in itself and look after the one. And I guess it's protective, it's evolutionary, and we haven't quite gotten to the other end of that evolutionary pattern of survival, of being on our own. Yeah.
Yeah, but we do see that communities are stronger than individuals by themselves. And we do band together in communities for a reason. We just have to recognize the global community as best we can.
No, absolutely. That's beautiful, beautiful, beautiful. So I guess before we finish here, how can we help? How can you have your answers, your big questions answered? What do you need? What are the things that you require, or what you see for big questions that will make such a big difference for us, really, for the whole planet?
Yeah, well, I think support for basic science from the community is really important. So support for science in general and for research, because we see how it improves our lives in so many ways. Support for basic science, the sort of fundamental research that you don't see is necessarily going to have an impact in the immediate future, because you don't know what it's going to discover. So, people playing around with wires and magnets probably didn't realize that we're going to have a whole economy and lifestyle built on electricity. They're like, oh, look, cool, isn't this cool? This makes this move. Right now, we don't know what is going to happen with dark energy and dark matter, but maybe it will form a new type of clean energy. So that kind of thing would be the ideal situation for me. But along the way, we also come up with all sorts of different cool things. So some of the group that I was working with supernovae, like to discover supernovae, you take repeated images of the same patch of sky and see what changes. And they've changed that into, they're developing an app that can be used to look at moles and have people take repeated photos of moles and see if things have changed. There's one of my colleagues designed a radiotherapy device that rolled the patient instead of moving the beam. And that was made possible by astronomy technology that took into account the movement of the atmosphere and was able to actively adapt mirrors to realign things so that it adapted for where the organs are moving as the person rolled around. Some of my other colleagues have gone away from astrophysics and used the data science stuff that we're doing to optimize energy grids for the best supply of clean energy. There's so many different sort of ways that things that you wouldn't necessarily ever have thought would come out of astronomy, but by supporting the basic research, all of these spin-offs sort of happen. And it's like increasing that base level skill, knowledge, fundamentals of the world, then goes out and improves our lives in so many ways.
Yeah, it's seeing the expanse of what's possible by not just working on one particular, question, as you said. There's so much more that can benefit from that, and the awareness and spreading the awareness around that. So then the correct funding can be put into places so we can get more of that. So
yeah, there's an enormous demand for physics graduates at the moment. And actually, one of the things when I'm talking to parents whose kids are interested in astronomy, and they're like, "Oh, my son or daughter is really excited about astrophysics, but there's no jobs in astrophysics. I don't know what to advise them." I'm like, "What are you talking about?" There's every single person who graduates from a physics or astrophysics degree is just snapped up by consultancy companies, by data science companies, there's people in the medical industry. There's such low unemployment for people with physics qualifications, because what it teaches you to do is take real world problems, optimize them, and find the best solution. using maths. And that just applies in so many different fields.
Absolutely. I think my son will be one of those. Might be pushing him over to you.
All right. Sounds great.
Oh, thank you so much for your time. Is there anything you want to leave? But we always ask the question of, how you can live smarter, not harder in the podcast, obviously on theme. So if you wanted to add, like 3 or 5 or 2 or any components to that you either do personally, or how do we look after this earth and live smarter, not harder?
Now, the living smarter, not harder thing, I should have prepared something earlier, but the first thing that comes to mind actually is just like the life advice that I was given very early on, and something that I've used for a long time is you don't concentrate on any one thing, diversify. I play a lot of sport and do a lot of things outside, and a lot of the things I've learnt from there has been really important in my career. And so diversify and enjoying life outside of work is an absolutely critical part of certainly my practice. Yeah.
That's incredible. I think that's a beautiful thing and advice for anyone. And it's true. We learn so much outside of our work life and in our experiences. And that's where we get all of our, insights. So thank you so much for your time today. It really has been a pleasure. And I really appreciate your time to come on and explain to me some of the, basics, but they're huge, huge questions. But yeah, I really appreciate it. Thank you so much.
Thanks so much for the invitation. It's been great.
And have a beautiful rest of your day.
You too.
Thank you for joining us on another episode of the Smarter, Not Harder podcast. We are so grateful for Professor Tamara Davis for sharing her expertise and guiding us through some of these biggest mysteries of our universe, from dark energy to the future of cosmic evolution. So if you enjoyed today's conversation, we'd love for you to leave us a review, share, like the episode on Apple Podcasts, Spotify, or wherever you listen. And your feedback helps us reach more curious minds like yours. Also, don't forget to subscribe to our YouTube channel for more fascinating discussions as well. We hope this episode has given you a new perspective on the cosmos and relevance to our life on Earth and this beautiful life we have. As always, we'll be back soon on another insightful episode, continuing to bring you 1 cent solutions to those $64,000 questions. We'll see you next time.